In the first lecture in this series, you were presented with the following problem. There are 3,000 students in a high school. There are 30 students per room. How many rooms are there in the high school? Now you immediately deduced that the answer obviously was going to be 100 rooms. Now I am very fond of asking my students, how did you solve that problem? About 95% of the time I get back the same answer. Oh, I divided 3,000 by 30. I just took the 3,000 students and divided by the 30 students per room, and I got 100 rooms. But that's not really what I'm asking. What I'm asking is not what did you do, but why did you do it this way? Why did you decide that the way to obtain the correct answer was to take the 3,000 and divide it by the 30? Now I'd like you to pause the DVD for a moment and ponder that question. Why did you divide 3,000 by 30? Now, if you have difficulty formulating an answer to that question, you have a lot of company. It is a rare occurrence when a student can provide me with a clear, coherent, logical, sensible explanation as to why they chose to put the numbers together in that particular way. They just knew how to do this. It was just obvious to them that the numbers should be put together that way. Yet, believe it or not, the vast majority of chemistry problems that you're going to be asked to solve in a first-year high school chemistry class involve exactly the same kind of logic. The kind of logic that you use with complete naturalness and complete ease. Yet when presented with chemistry problems, many students have difficulty. Now, why is that? One reason, I think, is that few students have ever taken the time to analyze what they're really doing when they perform a quantitative operation like this. This is what I like to call a Gazinta problem. I mean, it's an old joke, but 30 Gazinta 3,100 times. But what's going on conceptually when you do this type of division? Basically, what we have here is the following. There are two numbers in this problem. There's 3,000 students and there's 30 students per room. What I'm going to say now is of absolute critical importance. In most chemistry problems, there are only two different kinds of numbers, just as there were only two kinds of numbers in this problem, 3,000 students and 30 students per room. 3,000 students is what I like to call an amount of something. You can close your eyes and picture 3,000 students, an amount of students. Similar quantities in chemistry might be 49.7 grams of something, or 3.88 liters or milliliters of something, or 9.15 moles of something. They are amounts of something. When you close your eyes, you see a quantity. 30 students per room is what I like to call a this per that. This per that means that 30 students are, for lack of a better term, packed into one room, a room holding 30 students. We usually write these things out in chemistry either by drawing a horizontal line between the numbers, or sometimes we may use a slash mark as shown on the screen. It all means the same thing. What we're actually doing in this Gazinta problem is trying to see how many times the 30 students per room will Gazinta the 3,000 students. Now, you've probably used that kind of logic literally thousands of times in your life, but you probably never have stopped to think about what you're really doing. Here's what you are really doing. You have an amount, in this case, 3,000 students. We could represent the students by dots. We won't actually show 3,000 dots, but if we did, we have a container holding a total of 3,000 students. We have a little package called a room, and in this room, there are 30 students. This room holds 30 students. Now, what we're really doing when we divide 3,000 by 30 is taking out of this school a little package called a room holding 30 students. Some of these students are now gone. Then we take out another package, another 30 students, and now more of them are gone. And then we take out another package of 30, and we keep taking out little rooms, each containing 30 students, until the students are all gone. That's what a Gazzetta problem is really all about. And chemistry is resplendent with Gazzetta problems. Anytime you are asked to solve some problems, there's an excellent chance that you will use this kind of logic somewhere along the way. Your ability to solve that students in rooms problem proves that your mind, without question, is capable of performing the kind of reasoning required to solve most of the chemistry problems you are going to be asked to solve. You don't need to be any smarter than you are plenty smart enough. What you need to be able to do is to take your natural ability to reason quantitatively, which you have amply demonstrated, and apply it to situations that you are not quite as familiar with. That really is the main goal of this lecture, to begin to show you how you can transfer your natural ability to reason quantitatively in everyday situations to problems that are presented to you in class. Notice I said begin, because this application, this transfer of ability from everyday situations to chemistry problems, is not likely to be fully developed by the end of this lecture, nor at the end of the next lecture. It's a skill that you develop over the entire series of lectures. It's a skill you develop over the entire course. Is dividing the 3,000 students by 30 students per room the only way that this problem could be solved? Of course not. In fact, I would say that if this were a chemistry problem, most students would not approach it by this logical, simple method. No, they would approach it by one of what we might call techniques. And the three most popular techniques for solving chemistry problems are: look for some kind of a formula, some kind of an equation that you can use, or use something called the proportion method, or use something called the factor label approach, or the factor label method, sometimes called dimensional analysis. The students in rooms problem could, in fact, have been solved by any one of these three methods. If you are already enrolled in chemistry, I strongly suspect that you may have already been inclined towards one of these three approaches to solving problems. Now, what would the students in rooms problem look like if we had chosen to solve it by using a formula? Now you might say, but I don't know any formula for students in rooms problems. Okay, but we can make one up. It's pretty easy. Here's a formula. ds equals ns over nr. That's a perfectly valid formula for solving students in rooms problem. ds is the density of students. How many students are in a room? Say 30. ns is a number of students, in this case 3,000. And nr is a number of rooms in the school. Now all you have to do when you use a formula is correctly line up the numbers with the three symbols in the equation and do the algebra correctly. So it might look like this. 30 is ds, 3,000 is ns, and I'm asked to find nr. So I set up a formula, 30 equals 3,000 divided by nr. And then I cross multiply, 30 nr equals 3,000. Then I rearrange the expression, nr equals 3,000 divided by 30, and lo and behold, I obtain the correct answer, 100 rooms. Is this a good approach? Well, I mean, it certainly worked. But I'd like you to think about this. If all we were ever going to do in chemistry is solve students in rooms problem, if that was it, then let's memorize this formula and we'll get an A. We will survive forever. But chemistry isn't just one formula. And what students try to do is to begin by learning a formula for calculating moles. Then they learn a formula for calculating density, and then there's a molarity formula, and then there's a stoichiometry formula, and there's a gas law formula, and there's this formula, and there's that formula, and there's the other formula. It's like trying to memorize all those rules for generating numbers. It's okay, just so long as the number of rules is very small, like the 2 rules we did earlier. But as the number of rules becomes greater and greater, it becomes increasingly difficult to keep them straight. We can do this just so long as the number of rules or formulas is small. But as the number of rules or formulas pile up, things become very difficult, perhaps almost impossible for many students. Eventually, it becomes far too difficult for most students to keep everything straight in their mind, and we eat that poisonous fruit. What about the proportion method? This is a very popular method with many students. Basically, it involves reasoning that goes something like this. The student says, this over that equals x over something else. If you were going to apply this method to the students in rooms problem, you'd probably say something like, one room is to 30 students as x rooms is to 3,000 students. You would then cross multiply and get 30x equals 3,000. You'd rearrange it to get x equals 3,000 divided by 30. And of course, you'd generate the correct answer, 100 rooms. So is this a good approach? Well, again, I mean, it certainly works. And I know a lot of students like it. But what I have to ask you is, why would you go through all of this trouble setting up a proportional equation, 1 over 30 equals x over 3,000, rearrange it algebraically, then solve the equation, when all you have to do is divide 3,000 by 30 to get the answer? Some students who are fond of this method will often respond, but I like this method, and doesn't it work? And when I say, yeah, it works just fine, they typically ask, well, then why don't we just use proportions? That's a very legitimate question. But the question I have to ask is, did you use proportions when you solved the students in rooms problem? And of course the answer, no, I didn't. So why didn't you use proportions on that problem? And the answer, I think, is very clear. Students will typically say, well, I didn't need to. What do you mean you didn't need to? Well, I didn't need to. I just needed to divide 3,000 by 30. And why go through all that work when it was obvious how the numbers should be put together to solve the problem? Well, of course, it was obvious in the students in rooms problem, and chemistry is just as obvious. Another very popular approach, probably the most popular, is the factor label approach, sometimes called dimensional analysis. This approach basically involves an analysis of the units on the numbers given in the problem. The assumption is that when a problem is set up, the units for the answer must work out correctly. Therefore, if you set up the problem with factors that have the proper labels so that the answer obtained has the proper units, then the problem is going to be solved. For example, if you wanted to work the students in rooms problem by using the factor label approach, your reasoning would go like this. Well, I'm beginning with the quantity 3,000 students. I must end up with my answer in rooms. Therefore, what I need to do to get my answer to come out in rooms is to multiply by some kind of a factor that has the following labels. Students must be in the denominator so that the students will cancel out, and rooms must be in the numerator, so I will end up with rooms for my final answer. And putting the correct numbers on this, it's 1 room for every 30 students. So once again, I generate the correct answer of 100 rooms. The factor label approach is the most popular approach to problem solving at the high school level. Textbooks love it, most teachers love it. And they love it for what truly is a very good reason. It is exceptionally powerful. You don't have to understand anything about what you're doing to get the right answer. All you have to do is analyze the units. And you make the assumption that if the units work out, the answer is correct. The problem could just as well have been stated in nonsense syllables or written in Egyptian hieroglyphics, which I assume you do not decipher. And you could still have obtained the same answer, which you would assume would be correct. That's its power. But to me, that's also its weakness. Because when you use the factor label too much, you're not forced to understand anything about what you're really dealing with. Indeed, the entire approach basically involves simply analyzing and canceling units. What the units actually